Something very strange is happening to our planet right now. The Gulf Stream is becoming unstable. The jet stream is threatening to collapse, the polar vortex could break apart, and even our Earth's magnetic field is going completely haywire. Is all of this just a bizarre coincidence, or is there a larger pattern behind it that could change the Earth forever? Today we're taking a look at some of the most threatening natural phenomena and just how serious the danger really is. And if this fascinates you as much as it does me, go ahead and subscribe to the channel right now. That way you'll never miss a new video again. And if you're already subscribed, you can really help this video by giving it a thumbs up. 5,000 likes should appease the YouTube algorithm. Let's start with a trend that could plunge us into an ice age: the weakening of the Gulf Stream. We keep reading reports that the Gulf Stream will soon dry up due to climate change and what consequences that would have for us. On the other hand, there are statements, for example from Sabine Hossenfelder, that climate change will not stop the Gulf Stream. So which is true? And what exactly is the Gulf Stream? Let's start from the beginning. The sun's radiant energy is the main factor influencing the Earth's oceans and atmosphere. This energy heats the Earth unevenly, with the tropics warming more than the poles. Warm air rises, cools in the atmosphere, and then sinks back down. This movement creates a phenomenon known as atmospheric circulation. The Earth's rotation, which further influences this process, contributes to the formation of the so-called prevailing winds, which are the main driving forces behind surface currents in the oceans. And it is the winds of the North Atlantic that shape the Gulf Stream. The wind-driven surface currents of the oceans are forced into an elliptical shape, forming a vortex between the continents bordering the Atlantic. This current vortex is influenced by the Earth's rotation, which, in conjunction with the prevailing winds, leads to intensified currents along the western arc of this vortex, thus giving rise to the Gulf Stream, which is approximately 50 to 150 kilometers wide and several hundred meters deep. It is part of an entire current system and can be found off the North American coast. It flows along the east coast of the United States and Canada toward the northeast, where it then merges with other Atlantic currents to form the North Atlantic Current. However, this also means that if the Gulf Stream were to stop, it would not mean that the entire North Atlantic Current would come to a standstill. The Gulf Stream is, of course, a major contributor to the North Atlantic Current, but there are also other currents that help transport warm water northward and influence the temperature, for example, the Canary Current along the west coast of Africa. But can these currents really just stop? And that brings us to the fascinating concept of the North Atlantic Meridional Overturning Circulation. The North Atlantic Current and the Gulf Stream are part of an even larger system known as the Atlantic Meridional Overturning Circulation, or AMOC for short. The AMOC is a highly complex system of currents that transports warm water from the tropics to the North Atlantic and carries cold, salty water from the North Atlantic to the southern oceans. This gigantic circulation system, which has counterparts in other parts of the world such as the AMOC in the Pacific, plays a crucial role in regulating the global climate by distributing heat and salt throughout the ocean and influencing the carbon cycle. Unlike the Gulf Stream, which is primarily driven by the Earth's rotation and the resulting winds, the AMOC is driven by thermohaline circulation. This is an extremely complex process in which warm, highly saline water is transported from the equatorial region toward the North Pole. There it cools and sinks due to its higher salinity. This forces cold, salty water down into deeper layers. The sunk, cold, and very salty water then flows back toward the equator in deeper ocean layers due to the higher pressure and density. Along the way, it warms up again due to more intense solar radiation, and as soon as the water reaches the tropics, it rises again and begins the cycle anew. And this process can be disrupted by climate change. As polar ice melts, the fresh water it releases alters the density of seawater. This can result in not enough water sinking to maintain the circulation, which in the long run could lead to a slowdown or even a complete halt of the AMOC, but we cannot say that with certainty either. Ocean circulation systems are influenced by countless factors, not all of which are caused by human activity, and we are still far from understanding all the interrelationships. A halt in the AMOC would, of course, also affect the Gulf Stream. It would change its course, but it wouldn't stop entirely. Perhaps it would even be a good thing if the AMOC were to stop. That's because less warm water would reach the north, which could help offset the effects of climate change in those regions and possibly stabilize ice loss in Greenland. The AMOC has already collapsed several times throughout Earth's history due to purely natural cycles regardless of what we do. Ocean currents are just one piece of the puzzle in this global chaos because something dramatic is also unfolding high above our heads in the atmosphere. The jet stream is also acting erratically. The jet stream is a strong, narrow air current in the atmosphere that circles our planet in large, wave-like bands. In the equatorial regions, the air is heated more by solar radiation than in the polar regions, and these temperature differences lead to the formation of high and low pressure systems. And since air always flows from an area of higher pressure to an area of lower pressure, horizontal air currents are created. Due to the Coriolis effect caused by the Earth's rotation, these air currents are deflected in an east-west direction, forming the jet stream. There are two main branches, the polar jet stream at higher latitudes and the subtropical jet stream at lower latitudes. As a global wind current, the jet stream is of course immensely important and has a major impact on weather patterns. It influences the direction of air masses, changes in temperature and humidity, as well as the formation of high and low pressure systems. And that's why the jet stream's current behavior might be seen as somewhat concerning. The southern part of the jet stream over North America has completely broken down. Instead of a continuous west to east flow, the jet stream bands are more undulating and exhibit deviations that lead to blockages and extreme weather events. Climate change could also be a contributing factor here. This is because when temperatures rise, even in regions farther from the equator, it alters the air currents between the equator and the polar regions. Without temperature differences, there is no longer such a strong distinction between the high and low pressure areas of the equator and the polar regions, resulting in weaker air currents and consequently a weaker jet stream. However, the currently looming Super El Nino could also be a contributing factor. Although it is initially only a local event, it has global implications because it alters ocean and wind currents. During an El Nino event, the normal temperature differences between the eastern and western Pacific are reduced, leading to a change in pressure patterns. This change affects the jet stream and can contribute to instability and fragmentation. As a result, the jet stream bands at higher latitudes are disrupted and deflected, which can lead to unusual weather phenomena. These changes in the jet stream affect weather worldwide. In some regions, they can lead to droughts, heat waves, or wildfires, while other regions face severe storms, heavy rainfall, and cold spells. These effects can be felt at both the local and global levels. And while we're on the subject of capricious winds, an invisible, icy guardian usually watches over the poles, the polar vortex. It is a large area of low air pressure and cold air that surrounds both of Earth's poles. In summer, the polar vortex weakens, and in winter, it strengthens. The term vortex refers to the air masses that circulate near the poles and are confined in a circular pattern by the jet stream. Since, as we know, Earth's axis is tilted, this gives us the seasons, as the angle at which sunlight hits the Earth varies throughout the year. And near the poles, this leads to the phenomena of the polar day when the sun never sets in summer, and the polar night when it never rises in winter. Since the sun barely reaches the North Pole in winter, temperatures there drop, especially in November and December. This occurs both at the surface and in the middle atmospheric layer, the stratosphere. The jet stream acts as a barrier to air transport and isolates the stratospheric air over the Arctic. The southern hemisphere polar vortex also extends through the stratosphere and into the mesosphere, but unlike the northern hemisphere vortex, it is stronger, larger, and more persistent. Furthermore, temperatures are colder and ozone levels are lower than in the north. However, as things stand now, the polar vortex may collapse. This is known as a polar vortex event or polar vortex disruption. As we've already heard, the jet stream is currently disrupted, which could allow cold air masses from the polar vortex to suddenly surge southward into lower latitudes. We're talking about frigid air masses that could suddenly reach almost as far as the equator. Even Florida, which otherwise has a Caribbean feel, could then be plunged into snow chaos as happened in 2022. In addition to climate change, however, there are other factors that can cause a polar vortex disruption. For example, when the pressure difference decreases because temperatures from the south are colder or temperatures within the vortex are warmer than usual. Global weather phenomena such as El Nino play a role here as well. Changes in solar activity also have a direct impact, since solar radiation is what keeps the entire system running in the first place. Paradoxically, a disruption can even lead to sharp, short-term temperature increases when warm air masses are suddenly displaced by polar air masses. Of course, a polar vortex disruption isn't the end of the world, and it happens regularly. However, there are indications that they are becoming more frequent. This is because rising temperatures in the Arctic could cause the temperature difference between the polar and mid-latitudes to decrease. As we've just heard, this so-called temperature gradient plays a crucial role in maintaining the polar vortex. However, it's not yet possible to say exactly when the next polar vortex event will occur. But the signs are mounting. A massive warming in the stratosphere has literally distorted the Antarctic polar vortex, with potential consequences for the ozone layer and weather worldwide. Normally, temperatures in the stratosphere over Antarctica in winter are around minus 80 degrees Celsius, but on July 7th, 2024, scientists were stunned when they looked at their measurement data. Temperatures in the middle stratosphere had suddenly risen by 15 degrees. On August 5th, there was another temperature spike, this time by as much as 17 degrees. Such sudden warmings in the stratosphere have massive effects on the south polar vortex. Instead of its usual round shape, it has stretched out and now looks like, well, a peanut. This deformation of the polar vortex is indeed highly unusual and could have far-reaching consequences for the entire planet. One of these consequences, by the way, concerns something you all know, even if you've never seen it: the ozone hole. Normally, the ozone hole begins to form over Antarctica in early August. This year, however, it was slow to appear. Researchers from the Copernicus Atmosphere Monitoring Service observed that instead of the typical pattern, where the ozone hole progressively deepens in August, it didn't develop until the end of the month. A strong, stable polar vortex causes extremely cold temperatures in the stratosphere. This cold is one of the prerequisites for ozone depletion, and thus for the formation of the ozone hole. However, when the polar vortex is weakened and distorted, as it is this year, these processes are disrupted. Now you might be thinking, yeah, great, no ozone hole, problem solved, but it's not quite that simple. The ozone layer protects us from the sun's harmful UV radiation. However, its annual thinning is part of the Antarctic cycle. If this cycle is disrupted, it could have unpredictable consequences for the global climate system. So no ozone hole isn't necessarily a good thing either. Great. But what caused the polar vortex to become so distorted in the first place? This brings us to one of the most fascinating aspects of climate research. Everything is interconnected. Scientists suspect that unusual weather patterns in the troposphere, the lowest layer of the atmosphere where weather occurs, could be responsible for the disruption in the stratosphere. In fact, July 2024 was unusually warm in Antarctica. For the entire Antarctic region, it was the 5th warmest July on record, and it gets even more complicated. Variations in sea surface temperatures and sea ice could disrupt these large-scale weather systems in the troposphere, which then spread upward. Imagine the climate as a row of dominoes. You set them all up, and then you nudge the first one. What follows is a complex chain reaction in which one domino knocks over the next. In our case, a slight warming of the ocean's surface may have affected the troposphere, which in turn disrupted the polar vortex, which then affected the ozone layer, and so on and so forth. The climate is, after all, a highly complex system. However, there is a strong suspicion that a single event contributed significantly to this anomaly. The eruption of the Hunga Tonga undersea volcano in the South Pacific in 2022. In addition to ash, volcanoes emit a variety of gases, including sulfur dioxide, hydrogen chloride, hydrogen fluoride, and carbon dioxide, CO2. These gases can spread throughout the atmosphere and affect both air quality and the global climate. In the case of Hunga Tonga, however, a large amount of water vapor was ejected into the atmosphere, and we know that water vapor in the stratosphere can contribute to the formation of polar stratospheric clouds, which consist of tiny ice particles and in turn create an environment where chemical reactions can occur that accelerate ozone depletion. In the meantime, however, this anomaly over Antarctica has subsided again. So what does all this mean for us? First of all, it shows how important it is to continue researching and monitoring our poles. The polar regions play a key role in the global climate system, and changes there can have far-reaching consequences, even affecting us here. It also underscores just how complex and delicately balanced our climate system is. A small disturbance here can trigger major changes elsewhere. And then there's perhaps the biggest challenge of all, our Earth's magnetic field. First of all, we need to distinguish between the geographic and magnetic poles. The geographic North Pole, and likewise the South Pole, is a fixed point, namely where the Earth's axis of rotation pierces the surface. The magnetic North Pole, on the other hand, is the point where the Earth's magnetic field lines enter the ground perpendicularly, and this point is anything but fixed. Ever since its discovery in 1831 by explorer James Clark Ross, we have known that the magnetic North Pole drifts. But in recent decades, this drift has taken on a completely new dynamic. Since the 1990s, its speed has increased dramatically. From a leisurely pace of about 15 kilometers per year, it has accelerated to as much as 55 kilometers annually. After drifting ever faster towards Siberia for years, the magnetic North Pole has suddenly slowed down again in recent years. In short, the magnetic North Pole behaves in a completely erratic and unpredictable manner. But why is this actually so important? The Earth's magnetic field is responsible for protecting us from cosmic radiation and the solar wind. Without this magnetic field, life on Earth as we know it would not be possible. The Earth's magnetic field originates deep inside the Earth in the outer core. There, at a depth of about 2,900 kilometers, lies a huge sphere of molten iron and nickel. This molten mass is constantly in motion and generates electric currents through its rotation, and these in turn generate the Earth's magnetic field. Scientists call this the geodynamo. Scientists do not know exactly why this strange behavior is occurring now. There are various theories, but none of them can fully explain the observed behavior. One possibility is that changes in the flow of molten iron in the Earth's outer core are responsible for the unusual movement. Another theory suggests that the movement of the magnetic North Pole is linked to changes in the strength of the magnetic field. Over the past 200 years, the magnetic field has also lost about 9% of its strength. That may not sound like much, but for geophysicists, it's a concerning trend. Some scientists even speculate that this could be the beginning of a pole reversal, a process in which the Earth's magnetic north and south poles switch places. Such pole shifts are not unusual in Earth's history. They occur on average every few 100,000 years. The last major pole shift took place about 780,000 years ago, so we're actually overdue. However, a pole reversal would not be a sudden event. It would stretch out over thousands of years, and we would have plenty of time to prepare for it. So it's safe to say that, from a geological perspective, a pole reversal is imminent. At least from a geological standpoint, to keep pace with changes in the magnetic field, scientists regularly update the World Magnetic Model, WMM. The model is crucial for many navigation systems, from smartphones to military equipment. Normally, the WMM is updated every 5 years. Currently, it's being adjusted annually. To give you an idea of why this is important, if you were to travel the 8,500 kilometers from South Africa to the United Kingdom in a straight line using an outdated WMM, you'd end up about 150 kilometers from your destination. So you can imagine just how significant the impact of these systems is on all our technology, and how vital research into the magnetic field itself is for our modern lives. I hope you've now gotten a fascinating but also somewhat unsettling overview of what's currently happening to our planet. I'll of course keep you updated on all further developments right here on this channel. So if you haven't already, go ahead and hit the subscribe button. It really helps me with my work. And don't forget to give it a thumbs up to help us reach 5,000 likes. And while we're on the subject of capricious systems, a veritable monster is brewing in the Pacific right now, an El Niño of historic proportions that, as we now know, will have drastic consequences for the entire world. You can see what's coming our way in the video in the top right corner. As always, there's another topic related to science and space in the bottom right corner. And other than that, I'd say see you in the next video. Take care, everyone.